Good morning. Today we're going to look at graphing functions. Yesterday we talked about domain, range, what is a function. Today we're going to look more into the graphs and how to tell if graphs are functions. You probably have used the vertical line test in some math class to determine whether or not a graph is a function. It's very simple. You use your pencil or ruler, hold it vertically, and if it goes through that graph at more than one point, it's not a function. So if we hold the ruler up to this one and we go across, it only crosses that function at one point at any time. So that would be a function. Here we have an ellipse. Doesn't matter where you draw your vertical line, it hits the graph at two different points, so that is not a function. So the vertical line test comes in handy when looking at graphs. Domain and range with graphs. So if you have a graph and you want to find the domain, you're looking at numbers that go side to side, left or right. How far does the graph go to the left? How far does it go to the right? For the range, you're looking at numbers up and down. So how far up does the graph go, or how far down does the graph go? So that's what we're going to be thinking about when we look at domain and range of a graph. So if we look at this one, how far left does it go? Well, it goes to -1. Well, how far right does it go? Well, it goes out here to infinity. So from -1 to infinity. Okay. Well, how do we write that? Well, normally we would write it x is greater than or equal to -1, because in this case, all the x's are greater than and equal to -1. In set notation, we included that -1 because it is a closed circle here. We use a bracket. -1 to infinity. Now we need to look at the range. So for the range, let's take a look at this. How far down does it go? Well, it doesn't go anywhere below 0. How far up does it go? Well, if you look at this graph, it has an arrow. It's going to continue to slowly rise as the x's get bigger. So it's eventually going to get to infinity. Okay? So the range would be all y values are greater than or equal to 0. And to write that, it's bracket 0, comma, infinity. All right, let's look at another one. This is a cubic function. And how do we know it's a cubic? How do I know it's a cubic function? It has two terms in it. Cubic is x to the third. If you subtract 1 from the 3, it should have two terms. Okay? Well, we know by the previous lesson that cubic functions are all real numbers for domain. Okay? It continues left and right forever and ever. It's going to keep going this way. It's going to keep going this way. And as a matter of fact, it's going to keep going up and it's going to keep going down, all going toward infinity. So the domain and the range are all real numbers. All right. This one is a piecewise function. So if we look at the domain of this one, it says x is less than or equal to -2. And if you look here at -2, it's going this way, all those numbers. Or x is greater than 2. This is an open circle, so we don't include the 2, but it's going to be greater than 2. So that's our domain. And it's written for you here in the notes. So let's look at the range. Well, nothing goes above 0. Nothing's up here. So everything's below 0. We've got a piece that includes 0 here, but doesn't include it there. So we have to include it because at least one of our values includes 0. So everything is at 0 or below. So that's y less than or equal to 0 or negative infinity to 0. We need to know where functions are increasing and decreasing. A function is increasing where it's going up and to the right. Okay? Up and to the right. So that's increasing. It's decreasing when it's going down and to the right. It could be increasing at multiple points or multiple parts of the graph. Same for decreasing. You can have more than one section increasing and decreasing. So we always look at these from the left to the right. Okay? So we're going to determine the interval where the function is increasing and decreasing. Up and to the right is increasing. So we have two areas that are increasing here. Decreasing is down and to the right. Okay. And we want to name these by the x values, only using parentheses. So this graph is increasing from negative infinity all the way to this x value, which is -3. So negative infinity to -3 is an increasing section. Here, from 2 to infinity, it's increasing again. So 2 to infinity, there's two sections that increase. Well, now we got to figure out where is it decreasing? Well, from these two, between these two x values, -3 and 2, it's decreasing. So we just write that as, it looks like a point, but it's actually an interval. So 2 rules of thumb here. Increasing is always up and to the right. Decreasing is down and to the right. Always write them with parentheses and always use the x values when you name them. All right, here's another one. And I don't know if you can see it real good, but this isn't actually a point. This is an arrow. Goes from here to here. Make it a little more defined for you. All right, so increasing up and to the right. Increasing here, increasing there. Decreasing is down and to the right. So it's decreasing here, decreasing there. So what are the intervals where it's increasing? it is increasing from -3 to 0, and it's increasing from 1, 2, 3, 4 to infinity. So -3, 0, union 4, infinity. That's the increasing parts. Where is it decreasing? All right. Well, it's decreasing from this x value, which is -4, 5, 6, -6, down to -3, and from 0 to 4. -6 to 3 and 0 to 4. Now we need to determine how functions become even and odd. A function is even if you replace every x by -x, and when you do the simplification, it ends up being the same thing you started with. And that has symmetry about the y-axis. Symmetry about the y-axis is if you take it and fold it along the y-axis, everything would meet. Okay, looks the same on the left side of the y-axis as it does on the right if you were to fold them and meet them together. A function is odd if you take a -x and you plug it in for every x value in the function, and the whole function after you simplify becomes a negative. Well, that's symmetry about the origin. Okay? If it's neither, there's no symmetry. And we're going to look at a few of these. So I'm algebraically going to calculate whether it's even, odd, or neither. To algebraically do that, I need to plug in a -x for every x in my function. So I'm plugging in a -x here and a -x here. If you have even exponents, the negatives stay a positive. If I do negative times negative times negative times negative, negative times negative is a positive, negative times negative is a positive, positive times positive is positive. It always works out to be positive if it's an even exponent. Okay? So that's going to be x to the fourth. Absolute value of a negative number, the negative goes away. So it all stays the same. It's the original equation that we started with. That means the function is even. Next one, if I plug in a -x wherever there's an x, and I do the simplification, okay? What's the exponent on the x? It's a 1, we just never write it. So if this is a 1 down here, that is an odd number. If it's negative, it's going to stay a negative. Here the exponent is a 2. This is going to become a positive. So we're going to end up with the negative of what we started with. If we end up with the negative of what we start with, that is odd. Next example, if we plug in a -x in place of the x, we get a negative x plus 6. The negative x plus 6 is not what we originally started with, and the whole thing is not negative because that would make it negative x minus 6. So this is one that works out to be neither. And here's another way you can remember odd, even, and neither. If you plug in a negative x and simplify, no signs change. It's even. All signs change. It's odd. And if only some signs change, it's neither. So write that down on your notes. It's a good way algebraically to remember it. No signs change, even, all signs change, it's odds. If only some of them change, it's neither. Graphing piecewise functions. You should have had experience with this in Math 3. So graph it one piece at a time using the domains that they give you. So for x plus 1, we're only going to use x values that are equal to or less than 2. Equal to or less than 2. So 2, 1, 0, negative 1, negative 2 would be some values that I would plug in. So if we plug those in, I'm going to get 3, 2, 1, 0, negative 1. It includes the 2. So I'm going to use a closed circle at 2, 3. I'm going to go to 1, 2, 0, 1. And my board is a little off. So I'm going to have something that looks like this for that little piece. For the other piece, 1 minus x, if x is greater than 2, we're going to use 2 in our calculations, but it's going to be an open circle and numbers that are greater. Okay, so if I plug in a 2 here, 1 minus 2 is negative 1. 1 minus 3, negative 2. 1 minus 4, negative 3. And 1 minus 5, negative 4. So I'm going to plot those on the same graph, but I'm going to use an open circle at 2, negative 1. 2, negative 1 is going to be an open circle. And my graph is really off here. All right, 2, negative 1. Right around there. And then I'm going to plot the other points. 3, negative 2. Right about there. 4, negative 3. Right about there. It's going to go down from there. So that's what a piecewise function looks like and how you graph it. Appreciate you listening in. Have a good day.